Okay, so now let's speak about a concept which is useful to know, which is the concept of state machines. So for a moment, we put this thing of the neurons, let's say, in pause for later. Okay, let's give an example in order to understand what this concept is. Let's consider this device. It's called turnstile. So if you want to get the train, you have to pass through this gate, but it's blocked, and so you have to unlock it by, let's say, putting a coin in this device. So you pay and then you pass. And then it's locked again for the next person that has to put the coin in order to pass. So we can describe this situation like this. So if we inspect this device, let's say that it has two states. One we call locked and the other one we call unlocked. So this is a state diagram and the circles are the states. And the arrows are showing how we pass from one state to another one. So we start from here. This dot is the starting point. It can be any, but let's say that we start from the state where this machine is locked. So how can we unlock it? We put the coin, so we are here, and this thing becomes unlocked. So this device has one input, which is the coin, the place where we put the coin. So once it's unlocked, of course one can put other coins in, but it doesn't change the state of this machine. It will be a waste of money, but the state will remain this unlocked. But this device has another input. It's an action that we can do on it. We can push the turnstile, and once we are in the unlocked state, if we push it, then we pass through it, and then it goes again in the locked state. This is the way this thing is done. And if we insist pushing it, so when we are in this locked state, it doesn't become unlocked. So we continue staying in this state. We never go back to the beginning. And this is the entry point of this diagram. The only way to proceed is to put a coin and then we go here. So the behavior of this device is completely captured by this state diagram. The states are defined, all the paths between the states are completely defined, and so because of this is called a state machine. So we might be tempted to think that all machines are state machines, but in fact they are not. Not all of them are state machines. So for instance, this simple Arduino can be a state machine, but it can also do things which are not according to a state machine. Why? Because it has inputs that are defined, not all the time are defined in this simple way, but they can be defined by the user in an unknown way. For instance, if you think of a computer, a laptop, so you have the screen, the keyboard, so you write on the keyboard and then things happens inside the computer. Then you read the screen of the computer, you think about something and then you write something else. I mean, very complicated things are happening inside the computer, but the fact is that the computer doesn't know a priori what you're going to input, and so it doesn't have a state diagram. It's a sort of open state diagram, so there can be things happening the computer doesn't know a priori. This doesn't mean that the computer will unable to react to those inputs, but in a way that a similar way that you don't know exactly what the user will input. Maybe sometimes the computer will not know exactly what's the sequence of things that the computer will do in order to, let's say, solve the problem you are asking, like by setting the inputs. So this creates a certain uncertainty, let's say. And this type of machines are not state machines because the states are not defined and all possible paths to the states are not defined. But now we speak about state machines. So another way of describing a state machine like this, beside telling the behavior with words and by writing a so-called state diagram, we can write a so-called transition table, which is this thing. So it's the table describing this. So it's organized like this. We have a current state in a column, the input and the next state. So for this is called transition state, and the output. So it is telling us what this thing is doing on the next step, the next state. We already met this sort of transition tables here when we will study the sequential circuits. So this is exactly a transition table because it tells us what the circuit is doing in the future, in the next time, respect to the current time, to the status of the current time. So here we have this example. So it's quite easy to read it. So if you are in the locked state and you put a coin, then the next state is unlocked. So the output will be to unlock the turnstile so the customer can push through. Then if it is unlocked, if it is locked and you push it, then the next state is always locked and the output is none. So you don't pass through. So you can basically read this table. So two different ways of describing things. So now I chose this example not because we are interested in getting the train and understanding the mechanics of this device, but because it follows a certain logic which we already studied, which is this one. So this is exactly implementing a flip-flop, because we put the coin and then the output gets unlocked. Then when we push the turnstile, we make it rotating, so we reset this device and the output will become locked again until we put another coin. So this is what it can be also written in a third different way, or fourth if you consider this schematic diagram, with a so-called algorithmic approach. So this one was a so-called architectural approach. So we have a piece of hardware, the way it's assembled, the way it's wired, it implements this logic which is written here or here. But we might also have an algorithmic approach in terms of computation done by a CPU, which is reading a program step by step. So it starts from here. The first step, the beginning, the entry point, is that the state is locked. So here we have a variable we call state that can have either two states, locked or unlocked, let's say 0 or 1. Then we have another variable we call turnstile, which is not pushed. So it means that nobody is pushing. And another variable we call rotator or rotation, which is false. So this is the preparation of the system. So by executing those first three statements in this algorithmic approach, we are here in this diagram. So nobody's pushing the turnstile is locked, nobody's putting the coin, and this thing is not rotating. We are here. This is just the preparation for this state. Then, if we have the evaluation of a conditional statement, so if the coin is inserted, then the state will become not locked, which means unlocked. If we don't do this, so else, the state stays locked. So we are describing what is happening here. So imagine a CPU with a program counter going time step by time step here and executing all those statements. Then it has to execute another check. So if the turnstile has been pushed and the state is unlocked, then you make the turnstile to rotate. So you set rotate the rotate variable to true, and according to this we change the state. So the state is unlocked. Else, so if all this is not happening, do not rotate. And then we have a return function with this goTo. Then once the program reaches this point, we want the program to go back at the step number 4 and repeat and repeat and repeat so on all these evaluations forever. So this is in a hypothetical pseudo language, like maybe basic language. So a language that I invented just in order to be more generic as possible. So you can understand that if we have this, like I have an Arduino like this, I can implement this logic for this turnstile by writing a program and uploading the program in the CPU. Then I connect one input to a sensor that will detect the coin, one output to an actuator that will unlock and make the turnstile rotate. But if we follow this approach, which is good, I mean there is nothing wrong with it. Imagine how many things we need. We need the clock, the program counter, the ROM, the arithmetic logic unit. So we need to build a CPU in order to do this. And imagine how many logic gates we need to do this in this way. And then for this very particular example, the same thing can be implemented like this, only with 2 logic gates. It's a big shortcut. So imagine that those things are neurons. We know that we can implement logic gates with neurons. So with 2 neurons connected this way, we solve the problem. That can be solved by building a CPU. So this is another way of thinking about neural networks. So it will be extremely redundant for us to build a neural network for a simple problem like this. So if we are smart, if we can find ways of optimizing our code, our logic, there might be sometimes, maybe not all the times, very straightforward, very fast shortcuts. So this is one possibility that we have to take into account, that not all the strategies, even if those are maybe more familiar to us, are the best in terms of usage of hardware or timing execution. And just to mention this, if we speak about brains, maybe nature through the neural networks found simpler ways to solve problems. but it might be difficult to us to understand what it did. But it gives you an interesting, let's say, insight about all these problematics. Okay,